Hello.
I think.
Yeah.
Is it at 2 o'clock or later time?
No, 2 o'clock on. 2.
Oh.
Neru, just check the YouTube audio. No? Okay. Yeah. Very good afternoon to everybody. Hey, cool. So here we are in the National Science Day third day session, an afternoon session. So I'm going to introduce Dr. Professor Mousumi Das, who is going to talk about in the galaxies and their black holes. So Mousumi Das is a professor at Indian Institute of Astrophysics in Bangalore. She completed her PhD.
Crispin, we can't hear you well.
Yeah, okay. Hello? Let me check. How is it now? I'm audible?
Now,
Yeah.
yes.
Echo is there.
Okay. Why? Hello? I'm audible?
Yeah, but there's still echo, I think. Can you hear me?
No, that's we cannot avoid because we both are at one place.
Okay, shall I? You want to introduce me here?
Okay, but
Come here.
no. For time being, you can leave audio to Mousumi and then.
Oh, I'll put mute, huh? I'll put mute.
No, mute won't work. Yeah, Mousumi Das is a professor at the Indian Institute of Astrophysics in Bangalore. She completed her PhD at Indian Institute of Science 1996. After that, she did several postdocs at Raman Research Institute in Bangalore and also at the University of Maryland in the USA. Since 2010, she Since 2010, she has been working at the Indian Institute of Astrophysics. She mainly works on galaxies to understand their nature through observation and simulation. Okay, now I'm giving, I request Mousumi Das to take over. No, it's okay. She can carry on.
Okay. Yeah. Can you hear me?
We can hear you.
Yeah.
Okay, thanks, Ishwar. Thank you. Okay, so good afternoon, everybody. It's great to be here on National Science Day, and it's wonderful to be speaking here. I'm going to take you this afternoon through a journey through galaxies and their black holes, and I hope you enjoy it. I spend a large part of my life studying them, and so I hope you will be able to understand the excitement from my talk. So we cannot talk about galaxies without introducing the basic building block of galaxies, and that is the stars. So the stars are the main component of galaxies, the component that we actually see. Sometimes a much larger, more massive component is the dark matter, but mostly what we see is only the stars. Now here in this image, I've shown you the picture of a star, which you can describe as a large ball of plasma, a self-gravitating ball of plasma, which is formed usually in the clouds, in molecular clouds, which I've shown here in the image below. And stars are not usually born alone. We know that in the universe, the main force acting is gravity. And gravity, as you will have learned even in your school, is an attractive force. So gravity will try to pull everything together with it. So stars, after they form, they will always try to form in clusters. And even if they have formed in small groups, they will try to merge with other clusters to form large groups of stars. The luminosity that we see in stars is what we measure and is how we look at it and look at them and trace their more clustering. So all of this is coming from the luminosity of stars, which is powered by the nuclear fusion reactions which happen right in the center of a star. Now, nuclear fusion, which does not happen naturally on Earth, is a reaction, a nuclear reaction that can only happen when the temperature is very high. And that happens inside the centers of stars. And when the temperature becomes high enough, then not only will you get hydrogen fusion, you will get the formation of even more complicated elements such as calcium and magnesium. Now, over this last few decades, scientists have understood that there are several nuclear reactions, and the most common one is called the PP chain. And the one that creates the most complicated elements, which are essential for life, are the CNO cycle and the triple alpha. So I've just to give you a flavor of what it looks like, I've given you an example of some of the reactions below. So you can see here hydrogen is fusing to form more and more higher atomic number elements. And what happens when you see the fusion of elements inside stars is that a little bit of the mass is converted to energy. And as we know from Einstein's equations, energy is equals to mc squared. So even a little bit of mass, when it's converted into energy, produces a huge amount of energy, and that powers the luminosity of the stars. And I'll come back to this later, because the same equation can be used to understand the energy that we are seeing from black holes. So the formation of stars is now quite well understood. It happens due to the collapse of clouds, dense clouds of molecular hydrogen. And when these dense clouds collapse, sometimes they will have a little rotation with them, angular momentum as we call it. And because of that, the clouds will begin to rotate. And as this rotation and contraction continues, we will finally find at the bottom here the formation of a star and the formation of planets around it. So the planets that we see in our universe are nearly always around stars. And this is because they are formed in the method I just talked about, the collapse of molecular hydrogen clouds, and finally the formation of rings. So stars are not alone. They are surrounded by a lot of debris. Part of that debris is the planets, and I've shown a picture here of the planets. There is also a lot of material in the form of fragments, and those are the asteroids, the meteors, and we know that a lot of this is in the outer parts of our solar system, in regions called the Oort cloud, the inner Oort cloud, and the outer Oort cloud. Now, the stars themselves have a different variety, depending upon their mass. They can be massive stars, O-type stars, B-type stars. If they're smaller stars, like our sun, they will be a K-type star or a G-type star. And the really tiny dwarf stars are the M-type stars. So this is like a small introduction that I've given you to stars, just in case you haven't read about stars already. So now we'll move on to galaxies, which is the main topic of this talk. And whenever I talk about galaxies, I always like to show this image. And I hope you will remember it after this talk. This is an image of the Milky Way. And if you are in a place where there isn't much pollution, when the sky is pretty clear, a good place is near the sea or in a very isolated forest, or the best is, say, a cold desert. When you look at the sky, you may see a band of light across the sky. And that band of light is our galaxy. Our galaxy is a disk. It's composed of a disk of stars moving in circles around the center of our galaxy. Now, because the location of our sun's planetary system is above this plane, okay? So our Earth is moving above this plane. So we can kind of look down on the plane of our galaxy to see the galactic plane. And so that is what you are seeing in the sky. You're seeing the galactic plane, which is composed of lots of stars and dust. The dust is giving you these black patches over here. And this galactic plane, the image of the galactic plane, is what really, I think, inspired all the scientists in early times, specifically Galileo. He was the first person who made the telescope and showed that the galactic plane, or the Milky Way across our sky, is actually composed of stars. And this you will be able to see only if you are in a very, very, very clear place. So all of this is possible because our motion is a little out of the galactic plane. And I will just mention maybe 2 lines of history before I continue, because we should give credit to all the older scientists. I'm just mentioning a few hundred years ago, Immanuel Kant. He was a German scientist who showed that we are moving around the center of the Milky Way, and all the stars are moving under their mutual gravity. He also suggested that the fuzzy patches in the sky were actually other galaxies. And this is remarkable because for those days, to be able to understand the concept of our galaxy and other galaxies is very, very remarkable. Later on, within 100 or 200 years of Kant's discovery, there were several other telescopes which were developed, and they all found that you could actually catalog all these stars in the night sky. And this painstaking work was done by Messier. Another catalog was by William and Caroline Herschel. And another one I would like to mention is by Dreyer in 1895. So I've just given these examples to tell you that what you see now in astronomy is actually coming from several years of a lot of hard work with cataloging. The real revolution, you could say, though, in understanding galaxies happened with the advent of photography. And this is because when you have a photograph, you have something which you can measure. Before that, scientists used to look through the telescope and make detailed charts about the positions of planetary and other celestial objects. But it's only after photography came that they were able to take hard copies, hard records. And this was very important because with that, measurements about galaxies could be made. And I'm not talking about a lot of the early controversies which happened maybe as recently as 100 years ago. These controversies wanted to know whether our galaxy was the only galaxy or there were other galaxies like Andromeda and M33, which appeared like fuzzy patches in the sky. So in about the 1930s, you could say it was fairly well established finally that ours was not the only galaxy. And hence you can say that was the birth of the field of extragalactic astronomy, because extragalactic means there are galaxies beyond our own galaxy. Now, after the 1930s and 40s, the other interesting development was that many other wavelengths were used to understand the celestial objects and galaxies. One of them was radio astronomy. And radio astronomy comes from the fact that all over our universe, from the night sky, we are receiving radio signals. Now, some of these radio signals could be from extraterrestrial life, but most of these radio signals are coming from other galaxies. And this is very important because it helped us measure the nuclear and the disk activity, the whole activity of other nearby galaxies. So for a good example, I've given you a picture of this wonderful Indian telescope, our own telescope called the GMRT, the Giant Meter Wave Radio Telescope. It's one of the largest telescope arrays in the world. And what it does is it looks at our universe at low frequencies. By low frequencies, I'm talking about meter wavelengths. And so this telescope is very well renowned internationally and is producing wonderful science. So now we've established that to understand fully what happens in galaxies, what we need is a multi-wavelength approach. So for example, if you look at a nearby nebula, Crab Nebula, which has a very active pulsar at its center, then you can see that in radio, its appearance is drastically different from what you see in gamma rays. In gamma rays, which is high energy, you can see the bright heart of Crab Nebula, whereas when you go to microwave and radio, you see the less energetic photons, but over a larger field. So this is the same for galaxies. To really understand galaxies, you also need a multi-wavelength approach. You need to look at them in X-rays, UV, as well as radio and infrared, and of course in optical. To do all these observations, we need telescopes at various wavelengths because we cannot use one telescope to study a galaxy in different wavelengths. We'll need an X-ray telescope, which has to be in space. We need a UV telescope, which has to again be in space. But we can use ground-based radio telescopes as well as visible telescopes. A good example being the one that we have in Hanle, Ladakh, the Indian telescope from the observatory run by IIA. So now that we have decided, or I have shown you that galaxies have to be studied at different wavelengths, I'm going to show you this Hubble Deep Field. And here you can see galaxies of all sorts. They look like little jewels in this picture. But one thing you can make out is that some of them are very compact, like this bright orange one in the corner, and some of them are diffuse with spiral arms. So looking just at this picture itself, you'll be able to make out that galaxies are not of one type. And basically, they look as if they are fuzzy, elliptical-like systems, or they are spiral, disky systems. And this is basically the two types of galaxies that we see in our universe, and they're very distinct. And they're distinct because of two things. One thing is that their composition. The composition of galaxies is mainly stars, which we all know, gas, mainly hydrogen, neutral hydrogen, as well as molecular hydrogen. Then there is also dark matter, which I will not talk about today, but which is one of the biggest mysteries facing scientists today. Then there is the hot gas, which comes mainly from star formation. And there is also finally dust. So all these components make up a galaxy. Now the components are different for an elliptical galaxy and a spiral galaxy. But before I tell you a little bit about that, let's just see one of the basic physics difference between an elliptical galaxy and a spiral galaxy. The basic difference is that a spiral galaxy is basically a disk. And that disk, just like a thali or a plate, is rotating. And the rotating disk of stars is embedded in a larger halo of dark matter, but appears in the sky as a disk. Now, sometimes that disk, because it is projected in the sky, it will appear elliptical in shape. But when we want to study it, we have to again deproject it. The difference between the elliptical is that the elliptical galaxies have an ellipsoidal shape. They don't have rotation. So elliptical galaxies are not supported against gravity by rotation. Instead, they are supported against gravitational collapse due to the random motion of their stars, whereas disk galaxies are supported against gravitational collapse due to the centrifugal force which comes about when particles or stars move about in disks or in circular motion. So now that you know the kinematic difference and you know also how they look, I'm just quickly going to tell you what is the basic properties of spiral galaxies first, and then I'll talk about elliptical galaxies. Because only when we know their structure can we start to understand the nuclei, the really heart of galaxies. So as I mentioned before, the stars are moving in rotating disks, in these rotating disks which are shown here. At the center of a spiral or a disk galaxy, there is what is called a bulge. And a bulge is basically like a sphere, like a football, you could say. And all of this structure is embedded in a kind of spherical dark matter halo. We are still not sure what the dark matter halo shape is, but we can just assume it's spherical for now. And within this dark matter halo, you get these innumerable number of small, tight clusters called globular clusters. And sometimes stars can escape from these globular clusters or from the disk. And so we can have also some randomly placed stars which are moving in orbits around the center of the galaxy. So this is basically the structure of a spiral galaxy, and it's the structure of our own galaxy, because our own galaxy, the Milky Way, is a spiral galaxy. It's a disk galaxy with spiral arms, hence we call it a spiral galaxy. Now, when you look at a spiral galaxy, the spiral arms are very interesting and they look beautiful. They look luminous. Now, there's a very simple explanation why they come about, and that is because of rotation. Now, if you see a disk rotating and it's rotating away from you, one part of it is rotating towards you, another part is rotating away from you. Now, if different radii are moving differently, then you'll get what is called differential rotation, which is same as when you take your coffee or your milk and you stir it, then you'll find it all swirls in the cup. And if you drop some cream in it, then you'll find the cream gets sheared out into a kind of spiral structure. Something similar is also happening in disk galaxies, in spiral galaxies. And all of this happens because of rotation. Now, this rotation is not present in ellipticals. In ellipticals, which appear as kind of boring, fuzzy structures in the night sky, ellipticals don't have much rotation. So they are supported against gravitational collapse, mainly because of the random motion of the stars. And these stars move in what we call orbits or paths. They just move in paths. And some of the paths are circular, some are boxy, some are loopy. And these stars in elliptical galaxies are much older than the stars in spiral galaxies. And this is one of the main differences of spiral and elliptical galaxies. Now, you may think that they are a little boring, and they do look a little boring. Even when I was a student, I thought ellipticals looked boring. But the center of elliptical galaxies contain the most massive black holes that we know of. And that makes them very interesting, because now in the last few years, technology has enabled us to be able to study not just the emission from the nuclei of these massive elliptical galaxies, but also track the black holes, also trace the black hole in the centers of these ellipticals. So I'll come back to that a little later. I'd just like to mention again although these ellipticals look boring in visible light, they have in X-ray large halos, really big solid halos, not solid, gaseous halos around them. And this makes them at multi-wavelength very interesting. So all of this has come about only in the last 20, 30 years because we've been able to put in space X-ray observatories which have been able to map these beautiful X-ray halos around elliptical galaxies. So if you look at the galaxy I've shown below, on the right, there is this bluish halo that is in X-ray. But the actual stellar part of the galaxy is all the way in the heart. And I've shown by arrows, this stellar component of the elliptical galaxy is located, embedded in this really large, massive X-ray halos. So M87 is perhaps our nearest elliptical galaxies. And this galaxy has come in the newspaper a lot recently because we have been able to map the supermassive black hole at the center of M87. And this is a picture showing another similar galaxies, the Centaurus galaxy, which has these beautiful radio jets, which have been shown with these arrows here. And in the center, there is a supermassive black hole. So this is an example of why now elliptical galaxies are so interesting. So I've just put this slide up just for reference to show you the differences between the disky spiral galaxies and the elliptical galaxies. It's not just their shape, it's also their kinematics. One moves in circular orbits and the other one has random chaotic type orbits. The elliptical galaxies have these massive X-ray halos, while the spiral galaxies do not. A lot of the features, their morphology depends upon their evolution. But since there is limited time in this talk, I won't talk about their evolution, but you can always write to me and tell me. So I'll just show you some images of our galaxy, our Milky Way. We call it the Milky Way. And that's mainly because we can see the band of light in the sky, which represents the disk of our galaxy. So just as I mentioned earlier, our galaxy, the Milky Way, is composed of a disk. It has a bulge. It has all these globular clusters, tight clusters of stars in the halo, dark matter halo surrounding it. And it also has some halo stars. Now, when we look away from the center, from our own position around the sun, then we will be able to see a couple of things in our disk galaxy. One of the things we can see is the spiral arms. And that is mainly because of the velocity information that we can get from observations. Now, when we take the velocity information, we'll be able to get the distance. And the distance has shown that there are these spiral arms which are very close by to us. The nearest spiral arm is Perseus. We are embedded in Orion. And the other nearest arm is Sagittarius. So you could say we are embedded in the Orion spiral arm, and we have the Orion cloud nearby. And I think many of you must have seen the Orion cluster, Orion stars, the Hunter constellation of the Hunter in the night sky. So all of these are related to the spiral structure of our galaxy, which I've shown you over here. And all of this spiral structure is rotating in the disk. And the spiral structure, research has shown, is actually not a kind of a hard spiral structure that's moving like some solid object. It's a wave. It's a density wave, which is moving just like we see the waves moving on the ocean. So it's a density wave which is moving through the stars and creating more stars by compressing gas clouds of molecular hydrogen. So this is basically what the disk looks like. Now the neutral hydrogen is distributed all over our galaxy, and so I've given a bright picture over here so you can remember that it's all along the disk of our galaxy. The molecular hydrogen is more clumpy, and that's to be expected because molecular hydrogen is composed of two atoms of hydrogen, whereas neutral hydrogen is just 1. So you have more clumpy gas. And both molecular and neutral hydrogen is often associated with dust. Now you may be surprised to hear about the dust in our atmosphere. But dust in our galaxies is very important because dust acts like a bed where molecules of neutral hydrogen can come, and the catalyst is actually the structure of the dust, which allows the neutral hydrogen atoms to come together and form molecular hydrogen. So dust is essential. Another thing, dust, we've realized why it's so important is that dust causes what we call extinction. And that's because dust absorbs UV light from the stars. And because it absorbs and gives out in infrared, we can often not see the centers of many galaxies because the centers of galaxies are often covered in dust. So we have to use other wavelengths to understand. But dust is also very important in component of galaxy. Now I'll come to the black hole in our galaxy. And in the next few slides, I will describe this wonderful journey that Reinhard Genzel and Andrea Ghez. Reinhard Genzel was from Max Planck in Germany, the Max Planck Institute for Extraterrestrial Physics in Munich, in Germany. And Andrea Ghez was at UCLA in Los Angeles, USA. Now, both of them received the Nobel Prize for detecting the black hole in the center of our own galaxy. And it was a very hard experiment. And if you had told an astronomer 30, 40 years ago that they were going to detect it, people would have laughed because it was something that was seemingly so difficult to do. The reason why it was so difficult is that a black hole does not give out any emission. A black hole swallows light, but it really doesn't give out any light. So one of the only ways to actually detect a black hole is by measuring the motion of stars around it. So a black hole has immense gravity, and when stars come near it, their orbits will get affected. So the black hole will dominate the potential around it, and all the stars near it will move in the potential of that black hole, supermassive black hole. And that is the basic physics which worked in helping them detect the black hole. Because what they did was, both groups, one in UCLA and the other in Munich, is that they tracked the position of stars near the black hole in the center of our galaxy. So way back in the mid-90s, radio astronomers had detected a kind of a very bright star, some region from where they thought that there could be a black hole, from where they thought that the stars were being affected, that there was some emission. So these groups of astronomers, what they did was they started tracking the position of stars, and they did this by taking photographs, time-lapse photographs every week. And this is something we often do as children. We take, you can take an image and you can just zip through them and you'll get a feeling of how something is moving. Exactly the same principle was used by them. They tracked about 30 stars, and these are BE type stars. They are bright in infrared, and they used also models, simulation models, because once they had part of the orbit, then they could use computers to generate the rest of the orbit. And when you do that, you can work back, do the maths, and find out what is the massive object that is creating this potential. So this is the way really how they worked back from the orbitals, from the orbits of the stars. They worked back, found the potential, and from the potential, they found out the mass. Because we all know from physics that any mass gives rise to a potential, gm by r. So that's basically the same fundamental physics that they use to detect the mass of the black hole in the center of our galaxy. So it was not easy. They used a lot of very sophisticated techniques. They finally found zeroed in about 30 B stars. I think now they are tracking even more. And they found finally that the black hole had a mass of 4 million times the mass of our sun. So that's 4 into 10 to the power 6 times the mass of our sun. And now this is a very large project. It's called Gravity. And this project Gravity is now doing a lot more in-depth work on not just the black hole, but tracing also other physics, seeing whether other physics also hold near a black hole. And I'm just giving this picture to show you how difficult it was, because you see, when we look at the night sky and the sky becomes clearer and clearer, you get huge number of stars. And so you have to very carefully isolate the stars that you want to see and track their orbits in the center. And this is possible using several kind of special techniques called adaptive optics. And one of the techniques was called spectral imaging. So these are techniques that are widely used nowadays, but 20, 30 years ago, they were very new. So this was remarkable. Their achievement was remarkable. Now, the center of our galaxy also, apart from the black hole, it also shows a lot of other activity, and most of the activity is generated by the black hole. That's because when material comes near the black hole, it is affected by the gravity and kind of shred apart. We say tidally stripped or tidally shredded. So because of this effect of the black hole's mass, we can see a lot of streamers in radio, in X-ray, and even in molecular hydrogen gas. So all of this has been studied over the years. The Galactic Center is now a very important area of research. So let me now, since we have talked about our galaxy and the nucleus of our galaxy, let me now move on to the different types of galaxies that we see in the night sky. So as usual, because we like to always classify things, as you must know from biology, we have also tried to classify galaxies. And this classification does not always mean that galaxies evolve from one class to the other. It's just a simple classification scheme. And we call it a tuning fork because it looks like this. On the right-hand side, you have barred galaxies, galaxies with a elongated structure in the center called bars. And you have simply spiral galaxies, which have no bar. And on the left-hand side, you have the elliptical galaxies. And you notice here, the elliptical galaxies become flatter and flatter. And there is a kind of a code which kind of denotes their flattening. E0, which is spherical, all the way to E7, which says that the ratio of the flattening is 1:7. So this is what is called the Hubble classification or the Hubble tuning fork of galaxies. And they vary, all the structure of the galaxies vary from left to right. As I mentioned, the ellipticals look flatter and flatter. The spirals have bulges which can look smaller and smaller. So there is a lot of difference over the Hubble sequence. But there are two types of galaxies which are not really kind of covered by the Hubble sequence. One is the lenticular galaxies, or we call them simply the S0 galaxies. So the S0 galaxies have an in-between appearance. They have features which are similar to disk galaxies, spiral galaxies, but also similar to ellipticals. There is also the irregular galaxies, which, as their name suggests, have an irregular shape. We have barred galaxies, as I mentioned earlier, and I'm not going to go into this, but I'm just going to mention to you, if you are interested, that bars are elongated structures which are necessary to keep the galaxy stable. So if you have a cold disk of stars moving in a gravitational field, most likely they will try to form a bar. In some cases they don't. We are still trying to understand why. And in some cases, if there is a massive bulge in the center, the bar does not form. So barred galaxies are a large topic all into themselves. Now let me tell you a little bit about the clustering of galaxies, because you all know that galaxies are not isolated. In fact, the whole universe, because it is dominated by gravity, and gravity is an attractive force, we cannot expect systems to remain isolated. For example, if we have one galaxy and another galaxy goes past, its gravity will affect that gravity. And sometimes, as in the Stephens quintet, a system of 4 galaxies, which I'm showing you here, the galaxies come close to each other and they become trapped by the gravity, by their own gravity, they become trapped within each other, and then they form a group. So galaxy groups are very common. There are about 3 to 10 galaxies in each galaxy group. They're usually embedded in large X-ray halos, which comes from star formation, and they're moving usually quite fast. So sometimes if they're moving very fast, one of them can even take energy from the others and escape. Or if some other galaxy is coming nearby, they can be trapped. That galaxy can be trapped in the gravitational field of the group. Now, if you look at larger levels, then you come to galaxy clusters. Galaxy clusters have thousands of galaxies. And we are actually very close to a cluster called the Virgo cluster. And because clusters of galaxies are so massive, then the galaxies which are nearby are often falling into them. And that's what's happening to our galaxy. We are falling into the Virgo cluster. And the Virgo cluster itself is within the Virgo supercluster, which is composed of large systems of clusters of galaxies. So this image, it's a very famous image, and I wanted to show you. It shows that our universe has a sponge-like appearance. So you have clusters of galaxies all over, clusters and superclusters of galaxy all over in filaments and wall-like structures. And then in between, you have these huge empty regions called voids. And when you hear the term void, you know it means something that is empty. And so our universe, most of our universe is composed of voids in volume. The most of the volume on the universe is actually empty. The mass in voids is very little. They are huge empty regions which lie between the clusters and superclusters of galaxies. So this whole system together is called the large-scale structure of our universe. And in this large-scale structure, we are a small part, but we have neighbors. And I just showed a few pictures here to show you the neighbors. Here is our Milky Way, and our nearest neighbor, which is about 700 kiloparsecs away, is the Andromeda. We have the Magellanic Clouds falling into us because they're very close by and they got trapped in our gravity. We have also a lot of small galaxies, the Fornax, the Sculpture, NGC 147. These are all small galaxies which are nearby and kind of trapped in the gravity of our galaxy, the Milky Way, as well as Andromeda, which is also called M31. So now that you have seen that galaxies are always coming close to one another, it's very easy to understand that galaxies interact, they merge, and this causes them a lot of evolution. And this evolution is mostly triggered by tidal effects, the gravity between them, and also star formation. And you can see here the beautiful star formation in a merging system. We call this the antenna because it looks like the two antennae of a insect. This is called the antenna, or sometimes it's called the mice. And this whole system of merging and interactions is very important for the overall evolution of galaxies. Now, I've spent quite a while talking about how galaxies evolve, and I want to come back now to the nuclei of galaxies. And very quickly, let me tell you about what happens when the nuclei, or the black holes in the centers of galaxies, they start becoming active. Now, we say that a nucleus is active, or it forms an AGN, active galactic nucleus, when it's very bright. It's so bright that we cannot account for that emission by stars. So if we cannot explain this bright nuclear center by stellar emission, or the center of this elliptical galaxy due to stellar emission, then we say that there is an active galactic nucleus in the center. And these AGN are found in a very large fraction of galaxies, I think around 20% at least. And you can see that the energy distribution of an AGN, active galactic nuclei galaxy, is much more different than a normal galaxy. And so why is this? Why can a nucleus of a galaxy become active? Now this happens when the really massive black hole, and I'm going to call it supermassive when it has a mass which is larger than 1,000,000 times the mass of the sun. So 10 to the power 6 and above times the mass of the sun is said to be a supermassive black hole mass. So now when any black hole, supermassive black hole, starts to accrete mass, so mass falls onto it, most of it is eaten up by the black hole. That's gone. Once it enters the event horizon of a black hole, we can't see it anymore. But some amount of the energy, some amount of the mass is converted into energy. And that energy is shows up as the luminosity of the AGN. Now we have, over the decades of studying of AGN, we've come to realize that an AGN has a basic structure. And so I've shown a cartoon over here. At the center of any AGN is the supermassive black hole. Around it, there's a disk, just like our galactic disk, but very small. There's a disk. We call it the accretion disk. Beyond that, there are dense, compact clouds of ionized gas. Those are called the broad-line clouds. Beyond that, there's a torus composed of dust and ionized gas. And even beyond that, there are more clouds, which are called the narrow-line clouds. And when the supermassive black hole accretes mass, it gives out energy. Sometimes it gives out plasma. And that plasma comes out as a jet. And that jet you can see over here. Mostly jets coming from supermassive black holes, they are visible in the radio. So that's why we call them as radio jets. So this is the basic image of an AGN that we have. Now, as I mentioned earlier, the AGN gives out emission over all frequencies in the visible, X-ray, radio, infrared. And over here, I've just noted which region gives what emission. So for example, the visible mainly comes from emission from the accretion disk and the gas around it. X-ray comes from the corona above the torus, and the radio comes from jets or lobes, and the infrared comes from the torus. The torus, because it's made up of dust, it can also polarize the light. So now that I've told you about AGN, why is it so important? And why has the field become so important? And I wanted to show this slide just to tell you why we think AGN are interesting. The first is that detecting AGN explains the bright nuclear emission in the center of the galaxy. Otherwise, we couldn't understand why some galaxies' centers appear so bright, why quasars appear so bright in the night sky. The second thing is that detecting AGN is one of the only ways in which we can detect supermassive black holes beyond our galaxy. Because as you know, supermassive black holes don't give out any light. But if mass is falling onto a black hole, then it gives out some emission. So only if a black hole is accreting are we able to detect it. There is also another way, and that is the way our black hole in the center of our galaxy was detected. And that is by seeing the motion of stars in the gravitational field of a black hole. That's the other way to detect a black hole. But you can't do that for distant galaxies, because in distant galaxies, you can't see their stars. They're just so far away. So the only way to detect them, to detect external black holes, is by looking at AGN. This is why it's so important. And we can look at also particular emission lines from AGN. And I've just shown this because this is very important for researchers studying the emission, the spectra from these AGN. And if you ever study AGN, you will probably be doing that. Now, since I've told you now about our black hole, what its mass is, and also AGN, I'm now going to tell you about the recent very big discovery in astronomy, and that is about imaging the black hole in the nearest elliptical galaxy, imaging the black hole in M87. And this came out in the paper, and I hope I can explain it to you. See, M87 is an elliptical galaxy, which, as I mentioned earlier, is not very remarkable, but it does have jets. In fact, one of the jets is shown over here, the jets in radio. Now, its supermassive black hole was known to be very massive, about 10 times 8. And the accretion disk in the center of M87 gives out emission at radio wavelength. So the concept behind looking at the black hole in M87 was that since it's so nearby, and since it has an AGN, can we detect using radio waves the emission from the accretion disk in the heart of this galaxy? So that was the aim. Now, if you want to do that, if you want to detect this accretion disk, which I've shown, this is an artist's impression, then you would have to detect this bright yellow region, which I'm showing over here, because that's where the event horizon is. And that's where we think that the radio jets come out of. And this region is very rich in magnetic fields and very rich in plasma. So you're having a lot of electrons moving at supersonic speeds. And when they do that, they give out radio waves. And those radio waves can be imaged if we have a very good radio telescope. So that telescope, this amazing telescope, was called the Event Horizon Telescope. And this is the image of the region around the black hole of M87, which you can see here. Also shown here is basically the steps. They used an array of telescopes all over the world. They compiled the data using atomic clocks, correlated it, found out all the fringes, what they call the fringes or the peaks, and then they combined all the images to form the final image. So all of this was done using radio telescopes. And here is one of the radio telescopes that was used. It's called ALMA, and it's in Chile, South America. And over here is all the network of telescopes that they used all over the world. And you can see that there are telescopes in the Antarctic, and there are telescopes in Hawaii and North America, all over. Now, you may ask, why do you need telescopes all over? The reason is that it's not possible to build a very big telescope. It's just mechanically not possible. However, we can use many, many telescopes to kind of give us points, sample the space and put all those points together, like bit like dot to dot when we did as a child. We can put together all those images together from many places on the earth and create a single image. And that's what was done with a lot of heavy computer. So you see, technology, not simple astronomy, but technology also played a huge role in detecting the shadow of the black hole in M87. So a lot of this is covered in Wikipedia. I've just shown the image. And since we are running now short of time, let me now just quickly show you some of the research that I am doing with students here at IIA. So what we're trying to do is we're trying to detect not one AGN, we're trying to detect pairs and groups of AGN. And this happens when galaxies merge, because you see, when galaxies come close to one another and merge, their black holes or their bulges will also come close to one another. And so you get these kind of eye-like features. They look a bit like owl eyes peering out. So the nature of these nuclei can be different. They can be just simple AGN, or they could be star forming. And that is something that multi-wavelength data can tell us. We can also have triple AGN, and that's very exciting, because if you have clusters of AGN, then that will tell us a lot more about how supermassive black holes are clustering in our universe. And not only that, when supermassive black holes come very close to one another, they will give out gravitational radiation, gravitational waves. And gravitational waves from supermassive black holes are at very low frequency. It's a totally different frequency from LIGO, which detects stellar mass black holes. So if we want to detect another type of gravitational waves, we need to study these kind of sources. They also give out a lot of hot gas. As I mentioned earlier, hot gas comes from the AGN, from the supermassive black hole, ejecting out material, but also from the star formation. And this is a picture that shows that. It shows two nuclei over here spewing out lots of energy, lots of plasma. Plasma can interact with the surrounding medium, produce more stars, and basically throw out mass from the nucleus. Now, when this happens, we also see star formation near the nucleus. And so with the AstroSat, the Indian telescope, we have been trying to study these nuclei. And many people, many groups in India are doing that. Let me just tell you about our work. Now, our work has used the ultraviolet imaging telescope to study the stars around galaxies like the one I'm showing here. There are two nuclei here. There's star formation along these arms, these kind of spiral arms. And these arms become kind of bright because of the star clusters, which you can see in UV. And here you can see two kind of big bright star clusters, and the left one is coming mainly from the AGN. So we've been studying sources like this. You can see some more here. I've just shown you, for example. And let me end by talking about the triple AGN system, the 3 AGN, which we detected from Indian Institute of Astrophysics. A student, Jyoti Yadav, was the person who first detected it. And since I'm her PhD supervisor, and Sudhanshu Bardwe and Francois Coombs, our collaborators, we all helped her put it together and understand that it's a triple AGN system. So the galaxies in infrared looked like this, very beautiful, but very strong bulges here. And you can see a knot in the top arm. That knot was previously thought to be just a cluster of stars. But what Jyoti noticed was that this cluster of stars had a different velocity, and the nature was totally different from star formation. And so she was able to pursue this and realize that it was a triple black hole system. And so we got some press coverage due to this. We were interviewed on NDTV, which was so exciting, because having others to understand the excitement of our research was like so rewarding. So let me quickly show you what our actual research was like. This is the galaxy, and you can see the colors here. They denote the velocity. The velocity of this galaxy was different. That's because it was falling in. It was captured by the tidal arm of one galaxy, the massive galaxy, and it was probably stripped of its matter and was falling into the heart of the galaxy. And these are some of the diagnostic diagrams that we use to understand that it is another AGN. And we also calculated the black hole mass. We found that the third black hole, which was falling into the tidal arm, that had a mass which was only 10 to the power 7 times the mass of the sun, whereas the other two were much more massive, 10 to the power 8. We detected some bright jets of emission coming from the nucleus of the massive galaxy. That was also very exciting. So finally, why was it important? Now, it was important because, of course, it was one of 3 detections in the world, so that was nice. But it's also important because it's showing you the supermassive black holes can cluster. And that clustering comes because of the galaxy clustering and because of gravitational forces in our universe. And this clustering of supermassive black holes can give rise to a lot of hot gas and star formation in our universe. That's really why it was so important. So now let me just mention my summary. Galaxies are made up of 10 to the power 6 to 10 to the power 11 number of stars. That's colossal, but that means that they are massive, really massive structures. And there are two types of galaxies, spiral galaxies and elliptical galaxies. Spiral galaxies are disk-like objects, whereas elliptical galaxies are ellipsoidal. They contain, all galaxies contain black holes. Some of the massive galaxies contain supermassive black holes. When the black holes accrete mass, they give out enormous amounts of energy and they become what we call active galactic nuclei. And this AGN emission coming from the centers of galaxies allows us to study massive black holes beyond our own Milky Way. So AGN activity is accompanied by star formation, by huge outflows, and also by big jets of plasma called radio jets. And galaxy mergers can bring galaxy nuclei closer together, resulting in the clustering of supermassive black holes. So I think I'll stop here and take some questions.
Thank you, ma'am. Thank you very much. It was a mini galaxy tour to the galaxy and black holes. Okay, so Zoom participants, they can unmute and ask the question. And for YouTube, yeah, there is one question from Arun Kumar. He is asking that how to calculate the rotation speed of galaxies.
Okay, so the rotation speed of galaxies, it comes from either you have to take the neutral hydrogen in galaxies and plot the velocity at each radius against the radius. That is called the rotation curve. That's actually the best way to measure the rotation of velocities, using the neutral hydrogen as a probe. The other way to trace the rotation of galaxies is using some emission line like H alpha. H alpha is the Balmer line of hydrogen series. And so H alpha is given out from all parts of a galaxy, even in the outer parts. So you can also again take the velocity. And when I say velocity, this is the Doppler velocity with respect to the center of the galaxy. So you take the emission line or the hydrogen line and you find out the center of its emission. What is the velocity? That will give you the rotation velocity of the galaxy.
Okay, thank you. I mean, in added up to that, we know the standard spectrum line and how much differ.
Yeah, so these are all standard spectral lines, especially neutral hydrogen, and you can just add them up all over the galaxy.
Okay. Next question from Parth Sir. How does the WHIM, which were discovered recently by the group of astronomers as a proposed solution to missing baryon problem, so how do these objects are all found outside galaxy?
Okay, so I think when you say WIM, I think you mean the warm, hot intergalactic medium. So that's a very interesting question. Now you are asking about the missing baryon question. So the WIM, recently it's been understood that it's not just WIM that is important for fixing the missing baryon problem. It's also the CGM, the circumgalactic medium. So if you have a galaxy, any galaxy will have an ionized kind of a halo around it, especially the elliptical galaxies. And that makes up the circumgalactic medium, CGM. Beyond the CGM comes the WIM. And the WIM is usually in filaments connecting the galaxy with other galaxies and the large scale structure. So the WIM has been found to contain most of the missing baryons, but there is also a significant fraction in the CGM around galaxies. I hope I've been able to answer your question. That was a very good question. Thank you.
Okay, again, Arun Kumar asking, Ma'am, most of the galaxies are moving away from our galaxies. Why Andromeda galaxy are coming near our galaxy? And if it
Oh,
is due to gravity, then how much is the gravity of our galaxy?
okay. So actually, the Andromeda galaxy, as far as I know, is more massive than our galaxy. So I think it's the other way around. I think we are falling into Andromeda galaxy. So, as you said, gravity is the main force, and because of gravity, we are actually falling towards the Virgo cluster. But also because Andromeda is even closer to us than the Virgo center of the Virgo cluster, Andromeda appears to be falling towards us. Now, I can't tell you the exact infall velocity. It will be of the order less than 100, I think. Yeah, I can't tell you the exact infall velocity, but you're right. Because of the gravity of Andromeda, it does appear to be falling towards us. But as I said, it's probably we are falling towards Andromeda rather than Andromeda falling towards us.
Other general questions?
100 kilometers. 100 kilometers per second. That's the exact value.
Okay. Other deep into the question, if you have in depth of the subject, better you can communicate, ma'am, through email ID. Maybe I'll finish with one question. Patsada is again asking, how does things like frame of reference, locality, space-time works inside the black hole singularity?
Oh, inside the black hole event horizon. I don't know that actually.
Yeah, that's what I answered. So if it is in
Because
depth of thing, you can communicate in person.
yes,
Okay.
yeah.
This is like popular. I think
There are many
Zoom.
theories actually, but I would not be able to tell you an exact answer for that.
If any Zoom participants, you can unmute and ask relevant to the topic which we discussed. You have the option to ask directly. Anyone, you can use the raise hand option or you can unmute and ask. Okay, so if there are no questions, we can thank Professor Mousumi Das for having a mini tour to the galaxy. Thank you, ma'am. Thank you.
Welcome.